it's important to remember that in RLC circuits, the reactance or the resistance will determine the phase angle. As a result, when we look at the effects of AC on an RLC circuit, we need to remember that the capacitor will cause a downward shift in the total, the inductor will cause an upward shift, and the resistor will cause no shift at 0 degree. Now, because we can see the inductor and the capacitor are working in opposite directions to each other, we need to remember that if I want to determine my total reactance, that's X total, that is equal to XL wavy minus XC. Okay, this wavy minus means nothing more than taking XL and XC and subtracting the two from each other in order to get a positive answer. Another way of writing this is X total is equal to the difference between XL and XC. Now from maths you should know that these indicate that these two are subtracted from each other in order to get a positive answer. Now, reactance we determined is the apparent resistance of the inductor or the capacitor due to the frequency that it experiences. Because when it experiences a frequency, there's a phase shift, we need to incorporate that when we calculate the overall opposition to current. That overall opposition to current is called my impedance. Okay, now the impedance, if we look at these three, let's call them forces for now. If we look at these three, we can see that the resistance causes a horizontal, the inductor and the capacitor will cause a vertical displacement, XL on top, same as with the voltage, and XC at the bottom, the same as with the voltage. We can see from this that my total reactance is the difference between these two. So let's say XL is greater than XC, that is going to cause that to happen. Okay, if XL is greater than XC, then that X total will be above the resistor. That will cause this resultant to be above my resistance line. Conversely, if we look at a scenario where XL is smaller than XC, that means R is going to be over there, capacitive reactance, and we're going to subtract the inductive reactance from it, and that is going to cause that, that's two lines, so that's two lines, so that line's going to come out there, and my X total, or total reactance, is going to be indicated on the right over there, but below the resistor. Drawing this resultant in there, that will show the resultant angle. We will get to that at a later stage. Okay, so when we draw an impedance triangle, this is what it's going to look like if XL is greater than XC, and this is what it's going to look like if XC is greater than XL. Also remember to indicate the directions of rotation. Okay, now as we can see, what we've got over there in both scenarios is we have got the condition of a triangle. So when I want to calculate the length of this axis, or this arrow, or the length of that arrow, which is my impedance, which we're going to represent with a Z symbol, we use the formula Z is equal to the square root of R squared plus the difference between my inductive and capacitive reactances, or conversely I can use the formula Z equals R squared plus X total squared in order to calculate the impedance of this diagram. These diagrams are called my impedance triangle because we can clearly see that in both cases we are forming the triangle that represents the impedance with reference to my reference, which is the resistor. Now, in order to determine what's happening over here, in order to determine that specific angle, in both scenarios, that is called my phase angle. If I convert these diagrams to a phasor diagram, I will see that the current is on the horizontal axis and the voltage is in phase with my impedance. So, looking at mathematical concepts, we can see that the phase angle is equal to cos theta, which is the ratio between the resistance and the impedance. But because my currents in both cases are the same through the impedance and the resistance, I can also say that my phase angle is going to equal to the voltage across the resistor divided by my total supply voltage. And by applying normal maths on your calculator, you can then determine the angle at which the voltage will differ, or the angle between the supply voltage and the resistor's voltage. This is my phase angle formulas. Okay, I use these exact same formulas when I want to calculate the power factor. Okay, power factor is defined as the ratio between the actual power and the apparent power that is applied to the circuit. So cos theta is equal to the true power divided by the apparent power. Okay, now in order to determine my apparent power, I just say the total voltage multiplied by the total current, same as we did when we looked in grade 10. For the true power, because of the phase shift, if we look at the diagram, if we look at a power factor diagram, this horizontal is calculated by saying I squared times R. This diagonal is calculated by saying voltage total times I total. This vertical axis is my loss. This is the energy that the inductor and the capacitor is going to store. Okay, we'll get to that one a little later. So that is equal to that is equal to P, and that is equal to S. Okay, so P is calculated as I squared times R, because it's the only one that's in phase. Okay, now if I implement all of these together, then my true power can be calculated as P, which is equal to V times I, that's the totals, multiplied by cos theta, where that is theta and that is the phase angle. Alright.